Hello. Let's see now. We're going to start a new unit, which is going to feel weird because we're leaving stoichiometry without really doing an examination on it. And I want to assure you stoichiometry is not done. We're coming back around to it after an introduction into the states of matter and the gases. So if you're still feeling iffy on stoichiometry, or you're still feeling like you need some help, I think I'll post some examples of how to do each of the problems. And they are going to need to be, these things are going to need to be checked on or turned in at some point. But for now, I just want to move forward and enjoy all new topics, all new content just for us. And in order to get to gases, which is where I kind of want to be, we're going to need to do a really quick introduction to the states of matter. And we are only going to concentrate on the three states of matter that we're most familiar with here on Earth. And in order to do that, I want you to grab a piece of paper for your notebook. Yes, you're still going to want to keep your notebook. And I want you to divide that piece of paper or this circle into three sections. You can make your circle perfect, unlike mine, which is far from perfect. I guess I could make it perfecter if I spend a minute. But this is what I'd like to see, is a circle that's divided into three sections on your paper. And I want to think about some elements or molecules that you might be really familiar with. And I think I'm gonna choose water. I'm gonna choose water because water is the only molecule on Earth that exists naturally in all three states of matter. So let's write that down. What the heck? Water is the only molecule that exists naturally on Earth in all three states of matter. So that's interesting. So what does that mean? Let's think about that for a second. If we take each of these sections and divide them up by a state of matter, we could make one liquid, Liquid, and we could make one gas, and we could make one solid. And to do this circle, I want to add some arrows. And the arrows are going to be what we call it when we're moving from one state of matter to the other. So let's continue to think about water. If we're going to go from solid water to liquid water, what do we call that? Solid to liquid is, of course, called melting. And if we, on the other hand, go, and I want this arrow to be smaller, so you've got kind of a big arrow, and we can make this arrow sort of a reddish color, because I'm trying to emphasize that in order to go from a solid to a liquid, you have to add energy. You have to add temperature to get something to melt. So when we are going from solid to liquid, we are raising the temperature, and that's why this is red, and it's kind of a bigger arrow. When we go from liquid to solid, I want it to be tight and frigid, even though ice cubes are bigger, right? It's okay. We're going to have a blue arrow going the other direction here. And so what do we call it when we go from liquid to solid? We have to take energy out of that system and cool it down. And we're going to call that freezing. And I don't know how I'm going to write that in there because I did it too small. Let's see, freezing. So we melt to get from solid to liquid, and we freeze to get from liquid to solid, which is kind of obvious. We weren't all born yesterday. So now we're going to go from liquid to gas, and we're going to do our big arrow again. Let's get that baby in there, and we can make it red. And I imagine you're already thinking, what is that word to go from liquid to gas? What do we call that? And we're probably most familiar with that word when we're thinking of the water cycle, because this is, in a way, an extension of what you've learned about the water cycle. And that is, of course, it's evaporation. So water evaporates up into the atmosphere, and when it goes from gas to liquid, again, we're losing energy, so we're going to illustrate that with a smaller, tighter arrow. I'm going to be careful to try and make it not so small that I can't write in there. And that's a cruddy arrow if I've ever seen one. There we go. So if I go ahead and write this in, it is condensation. So condensation is what you see on the outside of your glass when you have ice water, let's say, in a glass, and then a lot of water collects on the outside of the glass. That's not water that just sort of seeped through the glass to the outside. It's actually water that is in the atmosphere that cools down enough to become liquid, and it'll just settle down on the outside of that glass of ice water and create a collection there. All right, now, when we go from gas to solid, this is the one everybody has the hardest time remembering because we don't see that so often. I'm going to do my two arrows right up front. So I've got, I'm going to remove these lines because I think it's prettier that way. I've got my red arrow, and I've got my other arrow to show more energy, less energy. Wait, from solid to gas needs more energy. Gas to solid, yeah. So we are going to need to change the direction of these arrows. That's probably something I should have not done, but there you go. Nobody's perfect. So we're going to show this arrow traveling this way. Why did I do that? And how did I make that mistake? I just I was following a trend and not really paying attention to what I was doing, I suppose. No biggie. So now that we have that into place, from going from a solid to a gas requires more energy. So we're going to call that from a gas to a solid, that's called sublime or sublimation. And we see from a solid to a gas, yeah, we see that happening in, I don't know if you've ever seen these, but there are in some bathrooms around the world kind of a little cone thing that is used as an air freshener. Some moms, some grandmas have those in their house. And you pop them open, and then this little gelatin solid that's inside of them disappears over time. If you've ever looked inside of them, it can take quite a while, but eventually it'll all be gone. This is an example of sublimation because the air freshener stuff never is liquid. It goes directly from solid to gas, and that takes off into the atmosphere, and it smells nice, and it's something that you would see in a bathroom, but not so much anymore. People have kind of gotten away from that. On the other hand, we also see from gas becoming solid directly, and we're going to call that deposition. And so there you go. We've got examples there of the 3 states of matter. And I know we're specifically talking about water, but some of the examples I gave you were for other things. What I wanted to do now is to just really quickly show at a molecular level the differences between each of these. And so if I start with liquid, I would have to create some particles. And these are just going to be circles instead of showing actual water molecules, because that would take too much time. And I know not everybody wants to do all that. So I'm just going to put some particles here, and they have some kind of surface tension at the top that keeps them liquid. However, on the surface of the liquid, of course, you're going to have some of the particles taking off into the atmosphere and becoming gas through evaporation. But in general, we're trying to illustrate this idea of a mass of stuff that's sort of settled down by gravity. Over here in the gas bubble, this will be fun. We're just going to fill it and evenly distribute gas particles throughout the space, because that's what gases do. They fill the space that they're in. And we're going to see that as we work into the gas equations that are coming up. I know you're excited about that. And finally, solid. We can do just a little chunk of solid right here, because solid is not going to be moving around. I mean, it does in a very small way, but it is going to be here like this. So there we go, solid, liquid, and gas. Water is the only molecule that exists naturally in Earth and all of the 3 states of matter. There is something else we need to, no, actually there's a couple things more we want to write. Sorry about that. And that is changes of state. Is the movement of particles in a phase of matter I'm writing energy, but there's other ways you can change the state of matter, and we're going to learn that as we move through. So when we think about particles and those particles moving around, they are carrying with them a certain amount of energy. And as we either remove temperature or add pressure or increase the volume of that matter, we're going to see some differences in the movement. They either will become more closely together and perhaps go from gas to liquid, and then from liquid to solid, or they'll move further apart. And the changes of state is going to look at that, and we're going to take some time and dive into how this matter moves around. But primarily what we want to be able to focus on is what is called the kinetic molecular theory of matter. And all that's really saying, I'll put a box around it just so we know that that's a thing. I'll make it a frame box because that's going to be fun to draw. And so this kinetic molecular theory of matter is based or focused on the idea that all particles of matter are in constant motion. And the way we kind of measure how quickly those particles are moving is actually temperature. It's something you're really kind of familiar with already. And so when we think about temperature in chemistry, we want to, let me see if I can move this a little bit. We want to focus on a measurement of temperature that's different for us. When we think about temperature, we think about, like today it's 57 degrees outside. And that 57 degrees is not the same temperature that we're going to use in chemistry class. We're going to use a unit of temperature that is called the Kelvin. And the interesting thing about the Kelvin, and its symbol is a big uppercase K. You can't do it lowercase or you're doing it wrong, so that's embarrassing. Don't do that. And the Kelvin temperature scale is based on the movement of matter. And there's something called absolute zero. And that is this point at which all matter stops moving. And so that's a zero, by the way. We call that 0 Kelvin. Because at 0 Kelvin, matter stops moving. And if matter isn't moving, well, we don't really know what happens at 0 Kelvin because as far as I know, it's never been reached. I know there are labs, there's scientists that are desperately or at least interested in figuring out what 0 Kelvin looks like. But to my knowledge, that has never actually happened. So what happens when matter itself, and that means like the matter at an atomic level, everything stops. 0 Kelvin has been, I guess, scientists have gotten very close to 0 Kelvin. They've just never actually reached that point where everything stops. You have to get something very, 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 very cold. So there is no temperature that's colder than 0 Kelvin. And I know that in our temperature scales, we talk about weather, and it was like 13 below zero and stuff like that. On the Kelvin scale, there is no below zero. Zero is zero, and that's the point at which matter stops moving. And so therefore, it's as cold as it can be. So there you go. I think that is what I wanted to talk about today. And I'll have a Google form for you to fill out. And tomorrow we will pick up and try to do a little bit more. All right, thank you.